Jurusan Teknik Pertanian atau yang dikenal dengan Agriculture and Biosystem Engineering atau AB merupakan salah satu program studi yang berada di Fakultas Pertanian Unila. Saat ini terakreditasi dengan akreditasi A. Beberapa bidang kajian yang ada di jurusan ini meliputi bagian-bagian yang mengarah pada Agriculture Industry 4.0 dan Agricultural 4.0. Di antaranya adalah desain alat dan mesin pertanian beserta aplikasinya yang berbasis IoT, misalnya perancangan berbagai alat mesin pertanian tepat guna dan berbagai pembuatan produk berbasis massa. Yang kedua, rekayasa penggunaan lahan dan air pada lahan kering dan basah yang ramah lingkungan dan berkelanjutan, misalnya pengolahan limbah dan hidroponik. Yang ketiga, rekayasa bioproses dan yang menangani pengolahan hasil-hasil pertanian, misalnya pemanfaatan teknologi near infrared dan teknologi spektroskopi, contohnya untuk pengolahan kopi. Kemudian juga penanganan nanoteknologi di bidang pertanian dan pangan. Yang keempat, sistem dan manajemen keteknikan pertanian yang meliputi antara lain teknik dan ekonomi penerapan Alsintan, pengembangan usaha jasa Alsintan, serta sistem dan manajemen.
Kenapa putus-putus?
Daya dan alat mesin pertanian. Yang kedua adalah rekayasa bioproses dan penanganan pasca panen. Ketiga laboratorium tersebut sebagai tempat kajian, penelitian, dan pembelajaran bagi dosen dan mahasiswa. Selain itu, jurusan Teknik Pertanian juga mengelola dua jurnal. Yang pertama adalah Jurnal Keteknikan Pertanian Lampung yang sekarang sudah terakreditasi Sinta 3, dan juga Jurnal ABE sebagai rintisan jurnal internasional. Jurnal ini sebagai tempat untuk mempublikasikan dan menyebarkan hasil-hasil penelitian dosen dan mahasiswa.
Halo semuanya, nama saya Aditya Adiwijaya. Jadi pada kesempatan kali ini saya akan mengajak kalian untuk lebih kenal dengan jurusan Teknik Pertanian Fakultas Pertanian Universitas Lampung. Let's go! Jurusan Teknik Pertanian atau yang dalam bahasa Inggrisnya merupakan Agriculture Biological Engineering merupakan jurusan yang ada di Fakultas Pertanian Universitas Lampung. Jurusan Teknik Pertanian tidak hanya mempelajari tentang mekanika mesin pertanian, namun juga mempelajari tentang sumber daya air dan lahan dan juga pasca panen. Jadi sekarang kita sudah di laboratorium A, yaitu tentang daya alat dan mesin pertanian. Halo Kak.
Halo. Ya, di sini laboratorium daya alat mesin pertanian atau yang sering mahasiswa teknik pertanian bilang itu bengkel. Di sini sendiri ini sebenarnya tempatnya untuk menyimpan alat-alat yang dimiliki oleh teknik pertanian seperti adanya traktor, hand traktor, alat pembuat pelet, dan juga mesin pengering-pengering lainnya. Selain itu juga lab ini sering digunakan mahasiswa untuk melakukan penelitian. Banyak penelitian yang dilakukan di sini seperti analisis mesin, pembuatan pupuk pelet, pembuatan papan partikel, dan juga pengeringan bahan-bahan hasil pertanian seperti vanili atau lada yang sering dilakukan di sini.
Baik, sekarang kita sudah di laboratorium yang kedua, laboratorium B, yaitu Laboratorium Rekayasa Sumber Daya Air dan Lahan. Yuk kita masuk. Halo Kak.
Hai, selamat datang di Laboratorium B, Laboratorium Rekayasa Sumber Daya Air dan Lahan. Di sini ada beberapa alat yang sering digunakan pada praktikum. Di lab ini ada, yang pertama itu ada magnetic stirrer, di mana magnetic stirrer ini berguna untuk mencampur atau mengaduk bahan pada tabung Erlenmeyer. Yang kedua itu ada prelabo. Prelabo ini berfungsi untuk memanaskan bahan untuk mengambil atau penyulingan. Dan kemudian di belakang saya ada lemari penyimpanan, di mana lemari penyimpanan ini untuk menyimpan alat-alat laboratorium yang tidak begitu digunakan. Kemudian di sebelah kanan saya itu ada tanur, di mana tanur ini berfungsi untuk menguji kadar abu pada suatu praktikum atau suatu penelitian. Dan kemudian ada oven yang berguna untuk menentukan kadar air pada suatu bahan. Kemudian di situ ada timbangan berguna untuk menimbang suatu bahan atau suatu alat yang digunakan pada praktikum. Terima kasih.
Baik, sekarang kita sudah di depan laboratorium yang ketiga, yaitu laboratorium C tentang laboratorium rekayasa bioproses dan pasca panen. Mari kita masuk. Halo Kak.
Hai. Ini adalah laboratorium bioproses dan pasca panen atau disebut dengan lab C. Dengan kegiatan yang biasanya dilakukan di lab ini yaitu seperti kegiatan teknik penyimpanan, teknik pengeringan, teknik pendinginan, dan teknologi pengolahan hasil produk pertanian dengan didukung dengan alat-alat seperti oven, UV spektroskopi, penetrometer, dan sebagainya.
Jurusan Teknik Pertanian Fakultas Pertanian Universitas Lampung mempunyai sebuah organisasi kemahasiswaan bernama Persatuan Mahasiswa Teknik Pertanian atau yang biasa disebut dengan Permatep. Yuk kita cari tahu lebih lanjut tentang Permatep. Halo Kak.
Persatuan Mahasiswa Teknik Pertanian atau Permatep merupakan organisasi kemahasiswaan di jurusan Teknik Pertanian. Permatep memiliki berbagai macam program yang menunjang kegiatan-kegiatan kemahasiswaan di jurusan Teknik Pertanian yang selalu bersinergi dengan jurusan Teknik Pertanian. Beberapa program kerja yang diemban oleh Permatep yaitu ada Desa Binaan dan Minat Bakat. Banyak sekali prestasi yang sudah diraih oleh rekan-rekan kita mahasiswa jurusan Teknik Pertanian, yaitu ada juara 3 Lomba Inovasi Teknologi Pekan Teknik Pertanian Nasional yang diadakan di Politeknik Negeri Payakumbuh, Sumatera Barat pada tahun 2019, dan rekan-rekan mahasiswa juga aktif dalam kegiatan program holistik pembinaan dan pemberdayaan desa yang dibiayai oleh Kemendikbud, dan masih banyak lagi prestasi-prestasi yang diraih oleh rekan-rekan mahasiswa jurusan Teknik Pertanian. Inilah kami, keluarga besar jurusan Teknik Pertanian. Mari berproses bersama kami dan berprestasi bersama kami. Tektan Jaya, Permatep bisa.
Assalamualaikum, terima kasih. Selamat datang Pak Dekan, Bu Melia, Pak Kadir, salam. Apa kabar Pak, sehat?
Alhamdulillah.
Alhamdulillah. Pak Budianto, sehat Pak Budi?
Sehat, alhamdulillah.
Pak Dekan belum muncul ini. Baik. Pagi Pak Dekan. Iya, kok gak iso Pak. Pak Ridwan, selamat pagi.
Baru duanya masih.
Ya. Selamat pagi Pak Kajur, Bapak-bapak. Salam sehat.
Iya. Itu Bu Elamida mana ini? Kok enggak muncul ini gambarnya?
Oh, ada Prof Abdul
Nah,
Kadir. Selamat
ada
pagi,
Pak
Prof.
Dekan kok enggak muncul gimana?
Alhamdulillah.
Selamat pagi Prof Kadir. Sehat.
Pagi juga.
Iya.
Alhamdulillah sehat.
Alhamdulillah.
Adinda Purba Seadiko. Purba Sanjaya.
Sehat, Kanda. Waalaikum. Iya. Masuk ya suara saya, Pak?
Alhamdulillah. Ya, rumah tua kita ini. Aduh, Pak Tusi sehat? Sudah?
Alhamdulillah sehat. Mas
Iya,
Adi.
sudah kelihatan kayak
Alhamdulillah.
orang Jepang sampean ini.
Oh,
Iya.
enggak, Pak. Masih
Tusi
Indonesia, Pak.
Tanaka. Iya, saya cek.
Aduh. Ini baru selesai praktikum, Pak.
Oh, siap. Kang Diding Suwandi, selamat pagi, Kang.
Pak Sandi, itu Pak Dekan sudah ada, Pak?
Ya, Pak Dekan, selamat pagi, Pak Dekan. Iya. Oh, belum muncul nih, Pak Dekan.
Assalamualaikum Pak Sandi, Pak
Waalaikumsalam, Pak.
Warji, kawan-kawan semua, Prof. Kadir.
Waalaikumsalam warahmatullahi
Pagi.
wabarakatuh.
Waalaikumsalam.
Waalaikumsalam, Pak.
Waalaikumsalam warahmatullahi wabarakatuh.
Monggo.
Iya, Pak. Selamat pagi juga. Selamat pagi, Bu Ainin. Yuk.
Good morning, everyone.
Good morning.
Good morning, everyone. First of all, I would like to say welcome to our Honorable Dean of Faculty of Agriculture, Lampung University, Profesor Dr. Insinyur Irwan Sukri Banua, MSI. The Honorable, the Head of Agricultural and Biosystem Engineering, Dr. Insinyur Sandi Asmara, MSI. The Honorable, Mr. Takashi S.T. Tanaka, PhD, as the guest lecturer. The Honorable, Mr. Ahmad Tusi, PhD, as the moderator. And the Honorable participant. Ladies and gentlemen, welcome to International Lectures on Agricultural and Biosystem Engineering with the theme Potential of Farm Experimentation Towards Digital Agriculture. It's a great honor. My name is Fitria Amelia Damayan. Will be your master ceremony for this extraordinary event. And let me read out our agenda this morning. The first, opening. The second, welcome greeting by the Head of Agricultural and Biosystem Engineering. The third, opening speech by Dean of Faculty of Agriculture, Lampung University. The fourth, guest lecture presentation. The fifth, award certificates and photo session. The sixth, closing. Ladies and gentlemen, the first agenda is opening. Let's open this event by praying to God. So, this event will run well from the beginning until the end. We invite all attendants to join the prayer, according respective religion and beliefs. Prayer begins. The second agenda is welcome greeting by the head of Agricultural and Biosystem Engineering, Dr. Insinyur Sandi Asmara, MSI. So, please welcome Dr. Insinyur Sandi Asmara, MSI.
Oke, thank you, terima kasih ya atas waktunya. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam
Warahmatullahi wabarakatuh.
Abi pun.
Ya,
Ya pun.
Very good morning to all of you. Alhamdulillah, praise to God the Almighty. Your Excellency Mr. Takashi Tanaka, PhD, invited speaker from Ibu University, Japan. Your Excellency Professor Dr. Insinyur Irwan Sukri Banua, MSI, Dean of Faculty of Agriculture, University of Lampung. All faculty members, students, alumni, and ladies and gentlemen, the participant of the International Lecturer on Agriculture and Biosystem Engineering, welcome to Lampung. Welcome to the Department of Agriculture and Biological Engineering, Faculty of Agriculture, University of Lampung. We are happy and very honored to host you all in this current international lecture. The main intention of the international lecturer on agriculture and biosystem engineering held in our department is to provide an international academic atmosphere in our department and our university. This international academic atmosphere is very important to elevate our university reputation in global higher education. This lecturer also will promote strong international research collaboration in our university. We believe that it will be a great contribution from our department to elevate our university accreditation. We plan to hold this international lecture only. Today is the fifth international quiz lecturer. Mr. Takashi Tanaka is one of the key persons in Faculty of Applied Biological Science, Ibu University. Will give us an important lecture on potential of farm experimentation toward digital agriculture. We also plan to invite many experts from Taiwan and other top universities to be our next quiz lecturer. I hope not only our students, our faculty members, but also our alumni will enjoy this international lecture. And Finally, our department would like to thank the Dean Faculty of Agriculture, the University of Lampung, for the continuous support of this event. On behalf of the department, I ask our Dean to officially open this international lecture. We wish you all have a fruitful and productive lecture today. Thank you very much for your kind attention. Wassalamualaikum warahmatullahi wabarakatuh. Thank you.
Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Dr. Insinyur Sandi Asmara, MSI, for the speech. The third agenda is opening speech that will be delivered by Dean of Faculty of Agriculture, Lampung University, Professor Dr. Insinyur Irwan Supri Banua, MSI. Time is yours.
Thank you, Fitria. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Tabik pun.
Ya pun.
Iya pun.
Good morning to all of you participants. Alhamdulillahirabbil alamin. Praise to God the Almighty. Your Excellency Dr. Takeshi Tanaka, invited speaker from the Faculty of Applied Biological Sciences, Gifu University, Japan. Your Excellency Dr. Sandi Asmara, Head of Agriculture and Biological Engineering Department, Faculty of Agriculture, University of Lampung, all faculty member, lecturer, student, ladies and gentlemen, the participant of international lecture on agriculture and biosystem engineering. Welcome to the Faculty of Agriculture, University of Lampung. We are happy and very honored to host you all in this current international lecture. I am very happy to report that the international lecture on agriculture and biosystem engineering have been well conducted 4 times since 2021. In those international lectures, our university invite many experts from Asia with different regions to share their advanced knowledge. The invited speakers from Malaysia, China, Japan, and Bangladesh deliver very interesting and inspiring lecture. In this month, I am very happy to support the 5th international lecture held by Agriculture and Biosystem Engineering Department. In this 5th guest lecture, Dr. Takeshi Tanaka from Gifu University, Japan, will share with us the potential of on-farm experimentation toward digital agriculture. The digital transformation of agriculture involves the adoption of digital technologies such as artificial intelligence, machine learning, the Internet of Things or IoT to enable new business model that can help improve agriculture yield, efficiency, incomes, and profitability. Finally, I hope this international lecture will promote academic exchange and international cooperation between the 2 institutes of University of Lampung and Gifu University. Ladies and gentlemen, by the name of Allah, the God Almighty, Bismillahirrahmanirrahim, I hereby officially open the international lecture on agriculture and biosystem engineering. We wish you all have fruitful and productive lecture today. Thank you very much for your kind attention. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Warahmatullahi wabarakatuh.
Thank you, Professor Dr. Insinyur Irwan Sukri Banua, MSI, for the speech. The next agenda is delivering lectures that will be led by our moderator. He was an undergraduate student and master student of Institut Pertanian Bogor and Doctor of Biological Production in Agricultural Sciences in Gifu University, Japan. Also, he has plenty of achievement. He has published 3 books, patent, and also prototype of a sprinkler portable for small-scale farmers. Well, please welcome Mr. Ahmad Tusi, PhD.
Baik, terima kasih Mbak Fitria atas perkenalannya. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Selamat pagi semuanya. Hello, welcome to the International Lecture Series on Agriculture and Biological Engineering events in this today. Good morning, everyone. My name is Ahmad Tusi, and I will be moderating this session. I'm super excited today because the Dean's already opening remark in this session. It's a very honor for us. The Dean can welcome in this session, so it will be excited for us to join in this session because this event about the international lecture today is very excited about all the amazing conversation that we are going to have today. Now, before we begin, let me remind you one thing. We won't be not recording today's lecture session. This is a space. This is a safe space for us. Here, there is no judgment, no repercussion, only unconditional love in this moment. Joining us today is a young Superman, I think, an amazing visionary man. And when I say amazing, I mean it. Today's lecture is about the on-farm experimentation toward to digital agriculture. Our speaker today is Dr. Takashi Sonamtashi Tanaka, or we call it Tanaka Sensei. He is a lecturer at Gifu University, Japan, on Faculty of Applied Biology. When I look in this, his CV, it's very awesome achievement by him. Tanaka Sensei has research interest and skill in agronomy, like a crop science. Also has ability in precision agriculture and spatial statistical nutrient cycling. Also, he's very expert in the machine learning, deep learning, satellite remote sensing by unmanned vehicle, and programming with MATLAB on Python. R is very tools. It's very helpful for us to analyze data. Also, he has experience in just now, is got new position as Group Research Center in Artificial Intelligence in Gifu University, and he also assistant of professor of Faculty of Applied Biological Science, Gifu University, and he has over 10 years experience in establishing data analytics for experimental on-farm experimentation. So I think this is a good person, good speaker for us today to talk about the experimental in digital agriculture. What's special about him is that he loves and establishing data analytics for on-farm experimentation. He will going to talk about the methodology as how to make use of on-farm data collection by digital tools in agriculture, like remote sensing and etc. Thus, on-farm experimentation will provide information about the better crop management on farms, how to share data between the farmers and the scientists. What is challenging to implement the on-farm experimentation with the digital agriculture? So this is the important for us to looking forward about it. Also, today, he will be sharing his top storytelling and pitching tips to help us with his farming experimentation, maybe with the digital agriculture in Japan, also in the other worldwide. Let's welcome Mr. Takashi Tanaka, PhD. Tanaka-san, you already joined me here?
Yeah, I'm here. Thank you. Thank you for your kind introduction.
Thank you very much for joining us in this lecture series, Tanaka Sensei. I hope you will be healed in better condition, because I heard last week you got the injury with your arm or leg, I forgot.
Leg. I walk too much.
So are you better now? Get well soon, Tanaka Sensei.
Yes, now it's better.
Nice. Tanaka-san, it's good so good to have you here. Now, thank you so much for joining us today. So I remind you all, the participants, the audience, our students, our colleges, before we begin, I have a few housekeeping notes. If you have any questions for the presenters, please raise your hand by click the hand icon on the Zoom tools, or say directly to us as your question. Or you can also write in the chat room if you with your favor. Yes, please, Tanaka Sensei.
Okay, so now shall I share my screen? There is no. Yes.
Yes, already since.
Sorry, now I can only see the final
I see.
slides. Wait a moment. Now maybe it's okay.
Okay.
Okay, now it's all right. Can you hear me?
Yes, I can hear you, and I saw your presentation.
Muted. It's all right.
It's all right.
It's all right. So okay, so
you can okay, sit.
Okay, let me start my lectures for 1 hour around. So today I'm going to talk about this topic about the on-farm experimentations. Maybe this word is not familiar with you. You are not familiar with this word, because this kind of experimentations in farmers' field is very prevalent in the European countries or in the US, but it's not so statistically feasible, or it's very challenging tasks to conduct experiments in farmers field in the Asian countries or any other developing countries, because we still didn't have much technologies to assess the crop status or the soil properties without the very hard working for collecting samples and analysis. But now there are a lot of the technologies to collect the data by using the, many kinds of sensors. So now we can easily implement many kinds of experiments in farmers' fields. So today I'm going to talk about how we could collect data and how we could polish or and apply this statistical analysis on the data that derived from the farmers' field. So first of all, let me introduce the backgrounds of the precision agriculture development. As you can see, this is a diagram of the flow chart of the precision agriculture technologies. So largely, we can divide the precision agriculture applications into 3 parts. The one is the data collections, and the second step is the interpretations, and the last step is the application. So first of all, we scientists or crop scientists or agronomists needs to collect the data from the farmers' field to give or provide some helpful information to farmers, how they could manage their fields. So first of all, we have to collect the soil samples to make the soil maps. I should use the razor pointer. Soil map. And of course, we can use some kinds of the remote sensing technologies, as you know, the satellite imageries or drones, UAV imageries. Then we can assess the crops growing status. So we can visualize the spatial variations of the plant growth. And the soil condition map and soil maps are almost the same. And here we can see in the Western countries, the yield map is very easily available because the large-scale farmers are now using the yield monitor that is equipped mounted on the combine harvester. So while harvesting the crop, at the same time, the farmers can know and understand how much yield can be attainable in each region or in each field. So these kind of data sets can be collected from the farmer's field. Then we need to integrate these different sources of data sets. Then we can use a kind of the model to understand the relationships between these parameters and the crop management and the impact of these factors on the crop yield. Then we can make the prescription map, how much fertilizers or seeds or the pesticides should be applied in each locations. So this kind of technologies in precision agriculture, we call it the site-specific management. So to implement this kind of the variable rates of the application fertilizers or the seeds, to implement the site-specific management, the agricultural machinery sectors are developing machineries that can conduct the variable rates fertilizer applications. And we always call it the VRA because we took this the first letters of the VRA. So variable rate application technology is very important in precision agriculture. So these kind of technologies are aiming to enhance the crop yield or enhance the crop productivities or the quality of the grains while reducing the environmental impacts. Because if we use a lot of fertilizers on the place where the plants grows very well, then maybe that plants can uptake a lot of the nutrients. But if that plants grows less than the other place, then we apply too much fertilizers, then most of the fertilizers could be leaked into the soil or to the groundwater. So it will cause the environmental impact. So, so precision agriculture technologies is aiming for both directions. The one direction is to increase the crop productivities, and another side is to reduce the environmental loss. So in this area, primarily, many scientists have only focused on the spatial variations of the crop yield or the soil spatial variations. But it's very difficult to identify the temporal issues. This is because we cannot repeat the same experiments or reproduce the same conditions for every year, because like Professor Tsushi is conducting experiments in greenhouse. Then we can control the outside environment, the ambient environments. Now we can control the climates, or according to the variable climates, open or closed, or the supply the oxygens, or maybe there are many kinds of the techniques to control the climates in a greenhouse. But I'm researching the crops growing in outside, like the rice, soybean, or wheat, and maize. In the upland fields or in the paddy fields, it's very difficult to control the climate. So we can observe spatial variations, and we can adapt some crop management according to that the variations, spatial variations. So the precision agriculture is aiming firstly to apply the new techniques, so like this kind of site-specific management, to enhance the crop yield in accordance with the spatial variations. And then, as you can see in this flow diagrams, the first step of the application of precision agriculture is just sensing technologies. So now here I'm presenting many kinds of the sensing technologies. For example, as I said before, the satellite imagery is very useful because we can assess a wide ranges of or the wide areas. On the other hand, the UAV, so-called drone, is very useful if you want to assess the crop health status in finer scale. Plus, the area for the capturing is very limited. We cannot capture wide ranges. On the other hand, there are also ubiquitous system of the sensing. For example, smartphone. As you know, maybe now everybody has the smartphone with the digital camera, and this digital camera is connected with the network. So if you take some pictures, then that pictures can be transported to the cloud services. And if you combine many kind of the services of the deep learning, then you could know, or the farmers could know, many types of the diagnosis. For example, in these pictures, if you take the leaf pictures with this a kind of the symptom of the disease, then the applications tells you about what kind of symptoms has been caused by in a specific disease and what we should do. And also the weather station is also a kind of sensing technologies. And this is also a typical case of the Japanese paddy field crop productions. This is the paddy field, and now some farmers started to use this kind of water level sensor. So in Japan now the farming scale is very enlarging. So a small number of people must manage a large area of the paddy fields. Then for every day, they have to check and observe the water level, but it's very tiring work, and they cannot control the water irrigations efficiently. So that's now they are started using the water level sensors. So according to this data, they don't have to go for checking the water level, or they can use the water very efficiently. And this is also another kind of the sensors. This is the NIR sensors, near infrared sensors equipped in the subsoiler of it's just back of the tractor. So generally, if you want to know the soil properties, we have to collect the samples and get it analyzed in the laboratories. So the process with the chemical analysis. But if you use this sensor, the soil properties data can be directly attainable as the spectroscopy of the NIR. So then if you have the supervised data, then we can predict how much nutrients or the physical properties contains in the soil on the go. It's very useful, and it can directly map make the soil maps. And one of the representative precision agriculture technology is just this one, so the yield sensor. This is the an example of the combine harvester equipped with the yield sensor. Maybe this is John Deere's harvester. So this kind of large harvester is now prevalent in worldwide to collect the grain yield. So now, as you can see, there are many types of the platforms of the sensing technologies in field. Maybe this is not only in the Western countries, but many sensors are now available in your countries as well. So I'd like to introduce the history of precision agriculture technologies. So for example, here, the yield sensor. Yield sensor is very old technologies. This history is available from this link. As you know, the yield monitor with GNSS is developed in the beginning of 1990s. So now it's 2022, so it's has the more than 20 years history of the yield sensors. And the variable rate fertilizer, the variable rate application technology is also not the new technologies. It's developed around 1995. And the section control, automatic section control. So I understand that most of the students are very interested in machineries in your department. So this kind of section control means is that this device can automatically detect how much fertilizer or seeds pesticides has been spread in the field. Then the controller automatically identifies such place. Then they stop the overlapping spreading of the resources. So this kind of technology is developed after 2000. And variable seeding, this kind of technology is largely applied in US. For example, for the maize productions or soybean productions, because of the price of the seed is not cheap. And if we could adjust the number of the seed or the plant densities to enhance the yield, then the farmers likes to change the rate of the seeding within the field, not in each field. So such kind of technology is also just in the beginning of the 2000 has been developed. So these sensors, not only the sensors, but implements to join with the machinery, agricultural machinery, is not all the technologies. These are developed more than about 20 or 15 years ago. So now we could see now, I heard that 40 or 50% of the US or the UK farmers are now using this kind of the yield sensor. Of course, it's very difficult to implement the variable rate application technologies. For example, variable rate application of fertilizer, maybe 10 or 20% of farmers are just using such technologies, but only concerning about only for the yield sensor, maybe half of the farmers are now using this kind of the sensors to know the yield variations. So for example, this is one of the example of Japan, Hokkaido. It's northern part of Japan. In Japan, also some farmers are now using yield sensors. So this field has the 4 hectares around, and this is the path, the working path of the combine harvester. And one point with the different colors indicates the crop yield. So every 1 second or every 2 seconds, the yield sensors are assessing the weight or the volume of the grain of the weeds. And we could see the large spatial defined variations of the yield easily. So, you know, this place, the red colors dots indicates a high yield. So we could know that this area is the potentially high yield areas. On the other hand, the blue color points indicates the low yield. So there are significant spatial variations of crop yield. This is the raw data. But if we process this data into the X and Y diagrams, then we can look at this data set as a kind of the matrix. So if you like to apply some machine learning models or the statistical analysis models, the data derived from the yield sensor is very useful. We just have to take kind of 2 or 3 steps for the data cleansing or denoising the data sets, then we can directly use them as a matrix data. Okay. And also, I like to introduce one of the example of the way how to make the prescription map. This service is provided from the startup enterprise from the Belarus, it's Europe countries. The company name is the OneSoil. This company is now using many kinds of satellite imageries, and it is automatically making the prescription map for variable rate application of fertilizer. So let's check this movie. I'd like to check it. So now you can select one of the polygons of the field, then what fertilizer you want to apply for it. So it is automatically analyzed the delineate areas or potentially high yield areas or potentially middle range of the yield or potentially low yield areas. So this on a cloud service automatically delineates the areas or management zones. And then the farmers or agronomists just only need to change the rates of the fertilizer. For example, the green area for 8 hectares in this area, I'd like to apply 60 kilograms per hectare of the nitrogen fertilizers. Then we can input 60. And for each item, we can apply the different rates. Then after making these decisions, you can download the files from this web browser, from web application. Then downloaded files can be transferred to the units of the console of the tractor. Then it automatically apply the different rate of fertilizers according to the place. So it's very easy, and the delineations can be made automatically by the algorithm of the OneSoil or any other cloud services. But here we have a lot of very serious problems. Sensing technology has been developed, and we could know how much yield can be attainable by using the yield sensors, but we still didn't know what is the best choice, how much fertilizer we should apply to each regions. For example, from the satellite imageries, we could identify 3 different types of the potential yield. Then here, this is one of the examples. For green areas, we put the 60 kilograms per hectare, but we still didn't know this is the best choice. So in the textbook of the precision agriculture, or generally the agricultural machinery consultancies often told us that we should increase the rate of the fertilizers by 20 or 30 minutes in potentially low yield areas to cover the low yield. But the problem is what kind of fertilizer or how much or when to apply. So there is no simple answer, because this the best answer will be variable across the fields or across the regions. So it's very tough matter. So then when we look back at this diagram, we have a lot of the sensors to assess the field conditions or crop conditions. Then we have many useful implements to apply the variable rate applications of seeds, fertilizers, and pesticides. And there are lots of the good equipments, but we still have many challenging tasks in the interpretations of the data sets. We can delineate the zone, which part is potentially low yield or potentially high yield, but how much or what kind of fertilizer should be applied or what kind of seeds or cultivars should be used in that field, is still unclear. So it is still largely depends on the farmer's experience or the local agronomist efforts. So the how and who analyze such data, on-farm data. So also what we call on-farm data is the data that is derived from the farmer's field should be analyzed. This is the challenging task. And we also have to summarize what we want to know through the on-farm data analysis or on-farm experimentations. Because this kind of the survey or experimentations or what we call the trials is aimed to enhance the crop yield in farmers' field. So, but if you increase, if we could increase, or if we successfully increase the yield or quality of the crops, then if we use too much fertilizers or we use too much resources or the cost, then the profit will be reduced. So every time, or we always need to remind that we have to understand how the yield or crop quality can be determined by the crop management or climate or soil. So this relationship should be formulated quantitatively. Without this modeling, we could know the best choice. So what we call the best choice is to increase or maximize the marginal profits of farmers. You know, the marginal profits is defined as the marginal revenue minus the marginal cost. So what we call the marginal cost is just the variable cost of the fertilizers or the pesticides and irrigations, the water cost. And the revenue is the crop yield multiplied by the crop unit's price. So what I want to emphasize here is that, yes, we could successfully increase the yield, but if we use too much fertilizers, then the cost will be increased, then the marginal profit will reduce. In that case, it's meaningless. So note that the yield maximization is not always the best choice. We are always needs to concern about the relations between the inputs and outputs, because agriculture and farming is also a kind of the industry, or farmers have to earn money for their life. So, you know, many crop scientists aims to maximize yield or maximize the qualities, but it is not meaningless for farmers sometimes. So how do we know the crop response? They're shown in the previous slides. If we could make model the crop yield response model to the crop management. So if we applied, for example, if we apply 10 kilograms per hectare of the fertilizers to the field, then we could gain the positively 60 kilograms of the grain yield. This kind of relationship should be modeled and estimated. So previously, all scientists prefers to use the small plot experiments to understand the relationships between the inputs and outputs. So this is because we don't have enough manpower, or we have to reduce the spatial errors of the experimentations. We scientists prefers to use this kind of small plot experiments to identify how much fertilizer should be applied to each or to specific cultivars in this small region. So we still have a lot of questions. These outcomes, the results of the experiments in a small plot experiment, can be directly returned to the fields in larger field, in actual farmers' field. It may not, we cannot use directly the same techniques or the same know-how to the larger field, because we only see very small parts of the field. For example, this small plot experiment is maybe if we compare with the US, the general Illinois farmers field, maybe only these areas. We use only these areas to conduct experiments, then we could get the results. But this area is occasionally high yielding areas. So this result can only apply to the high yielding areas, but it cannot be applied to low yield areas. So, there is a necessity to conduct experiments in large field to quantify, to understand the causal relationships between the inputs and outputs. So maybe you may have learned the statistics in the undergrad or joint undergraduate students. The name of the feature you may know if you are studying agricultural or the biological statistics. The Fisher, who is the statistician in UK, he developed the principle of the three principle of the statistics: the independence, and the randomizations, and the block design. So, what I want to add another aspects of the necessity of the small plot experimentation is that because it's very hard to apply the generally used statistical analysis such as the ANOVA, analysis of variance, to large field, because we cannot control the independency of the data because there are large special variations within the field. So the assumption of the ANOVA is not kept in the larger field. So we scientists prefer to use a small plot and randomized block design to testify our hypothesis or treatment effect using ANOVA. So there are two problems. One is very difficult to apply the general statistical analysis on larger field. Another aspect is that the small scale or small plot experiments cannot be directly applied to the field. But if we could solve two problems, so if we could apply the scientific way of the experiments in the field, in the farmer's field, so we called on-farm experimentations, can be implemented in the actual farmer's field, we could know the best crop management and practices in farmer's field in accordance with the regions or the soils or the cultivars. So many scientists now provide the scheme of the on-farm experimentations, and I'm just introducing it briefly. So the way of the flowchart of the on-farm experimentations is almost as same as the scientist experiments. First of all, we have to set up the hypothesis. So, for example, the new types of the fertilizers has the good effects on the crop growth, or like that. Or the if we increase the rates of the fertilizers, it could statistically significantly increase the crop yield or not. So we can set the hypothesis by discussing with the farmers or according to the local knowledges. And then we have to design the experiments. How many replicates or the randomization should be applied in that field. So, and hopefully we should use the randomized or the plots with many repeats in the field. But on-farm experimentations, we have to conduct the farmer's field. So it's very difficult to make the very small plots with many replications treatments. So we have to see the realities. And then the run experiments and collect data. So then if we have the digital tools in the Western countries or in Japan, now the yield monitor is available. So the collect data is very easy. And that's the setup for the experiments. What I mean, the variable rate of seeds or the fertilizer technology should be applied to make the complex experimental design. Without this, we can only use the simple design. So here, if we use the simple design, we have to focus on the efficient way of the statistical analysis. And me, I am very concerned about this area of the studies. So I am now focusing on the work of the statistical analysis for machine learning model to analyze the on-farm data. So this is one of the important scope of this scheme. And then after the analysis, we have to discuss the outcomes of the analysis to the farmers and repeat the experiments for the next year. What the problem should be solved in the next year. And here I have to notice that the objective of the experiments is quite different from farmers and the scientists. The scientist likes to know how much profits can be gained by changing the technologies or optimizing the technologies. But for us, scientists, we only could know the locally optimize the results, then we cannot write the papers or could gain the achievement. So we are more interested in the methodologies or the statistical approach or design of the experiments. So we have to note that we scientists and farmers are not the same. The way of the experiment is the same, but the interest is not the same. So for example, what we want to know field on OFE is just the simply to say, we just have to know the causal relationships between inputs, including fertilizers, seeds, and pesticides, or any resources, and the final crop yield and outcome. But there are two types of the statistical analysis. The one may make it important to see the significant difference. If you are a scientist, of course, I think you are agriculture students, and I am also a researcher. So we are more interested in the significant difference to publish the paper. If there is a difference, a significant difference in statistics, then we can say that this technology is the better. So scientists tend to regard significance as a very important factor. But maybe the farmers are not interested in the significant effects, or rather they are more likely to understand the quantitative effects. How much yield can be attained by changing the crop management? So we have to keep in mind these two aspects are different from the different position of the work. So here, now we are introducing two types of the on-farm experimentations, two types. The first one is to aiming the evaluate overall effects. So if we have this kind of 4 or 5 hectares of field, then we assume that if we change the rates of the fertilizer rates, then we could gain the 0.5 tons per hectare additional yield in the orange area. So in the orange area means the treatment plots. So if you run these experiments 1 year or 2 years or a couple of years after that trials, then the farmers can optimize their inputs without using the variable rate applications, because we are more likely to focus on the overall effect. So what the overall effect is that if you change the treatments or the crop management, that treatment effect is totally totally the same within the field. So this is the overall effect. And another types of the experimentation is to focusing on the site-specific crop management. In this case, as I shown in the previous slides, we can use the applications to delineate the field. For example, this blue line is the potentially high yield areas, and orange areas is the middle range of the yield, and the gray yield, gray scale, gray color indicates the area with the potentially low yield. In that case, each region may have the different crop response. So according to the assumptions, we should apply the different types of the statistics or the final implementations of the crop management. So if we only want to, if we are more interested in overall effects, we don't need to use the site-specific management like variable rate applications. But if we more interested in site-specific crop response, then we have to use the variable rate applications. So first of all, I'd like to introduce how we could use this overall effects and estimations. And I would like to introduce some case studies or the simulation studies and how we should design the experiments in farmer's field. So here, just I said before, we have learned from the statistics in the undergraduate students. Hopefully, the principles of the experimental designs are like this, like the design 5. We should increase the number of the replications, and sometimes we need the randomizations. In this scheme, we didn't show the randomizations, but the replications and the randomizations to randomize patterns of the experimental plots are the principle of the experimental design developed by the Fishers in the beginning of the 20th century, 1910 around. So if you only conduct small plot experiments in a research institute, we can apply the design 5. But if you are if you want to conduct on-farm experimentations, then sometimes we cannot apply this kind of the complex design. Maybe design 4 is also a little bit difficult to implement, but the design 3 is all right. If the farmers are using the machinery to spread the fertilizers, then after reaching at the headlands to turn around, then they just have to change the rate of fertilizers. So it's very easy to implement. So design 1 is also the same. Design 2 is also the same. So from design 1 to 3, well, we can simplify the design of the experiments, and maybe this method is very feasible for farmers to implement. But we still didn't know. So this kind of the method is robust. Can provide the robust statistical analysis. So because we learned that we should increase the number of replications and the complexity in the randomizations to reduce the spatial variations or to reduce the errors of the analysis of variance. So the design 5 may have more precise results, but the design 1 or 2 may have the less precise results as a result of the statistical analysis. So here, in the early century of the US, the US farmers like to conduct their on-farm experimentations. But at that time, they still didn't have the yield sensor. So like this, just after harvesting, the collected grains can be exported to the grain carts. But before putting into the grain carts, the farmers can use the weight wagon to know the grain weight. So what I mean is that if they can use the strip trial for each strips or each areas, the farmers can know the total grain yield. So because the selection of the corn hybrid is very important task for the US farmers to increase the crop yield. So many farmers have had this kind of experimentations to know the best cultivars. But this observation is just single. If you make the one plot, you could only know the one weight or one observation of data. But currently now the farmers are using the yield monitors like this. So yield monitors can generate many data points. So there's a huge task, a challenging task, how we should apply the statistical analysis on this massive, substantial points of the observational data. So if we only use the weight wagon, we can know this one strip's weight is about maybe 10 ton per hectare or something. But if you use the yield sensors, then we can know the every second recorded data. So maybe more hundreds or thousands data points could be generated from the single field. And these data are not independent. This is because spatially autocorrelated. So we should not apply the analysis of variance. So then what kind of a statistical analysis should be applied? This is very hot topic in recent precision agriculture field. But this is not the case only for yield monitors. If you use the UAV, it's almost the same. It provides much finer data points than the yield monitors, because yield monitor has the head working width is maybe from the 3 to 15 meters. On the other hand, if you use the UAV, then the data resolution is the maybe 1 centimeter or 2 centimeter, so it can provide much finer data resolutions. So if you use this kind of recently available remote sensing data sets, then it produces many spatial observations. So then, if you use the yield monitor, how many replications or the randomization should be applied? This is the question. So maybe you can read more precisely to understand this topic. I recommend that you read the paper that published by Alesso, and my papers are published in Precision Agriculture. We too are discussing the best experimental design using the simulation data. So, for example, now I'm showing the result from the research from the Alesso. This is the size of the experimental units. If we increase the size of the experimental units, how the precision of the experiments could be variable. So, for example, this is the RMSE. It means the precision of the experiment. If this value is low, the experiment is successful. So then, if we use this kind of very small plot size experimentations or the strip trials with many replications, it can successfully reduce the RMSE, the errors. But then, if you use the much simpler experimentations, it gradually increases the rates of the errors of estimations as an outcome of the statistical analysis. So if we conduct on-farm experimentations, we should avoid this kind of too simple experimentations. And hopefully we should use the strip trials with many replications, as many as possible. And here I like to show another interesting results from his work. So randomization is also very important, but in his study, as you can see, this is the systematic design without any randomizations. And this side is the randomized design. So the units of the experimental units size is the same for both, but the randomization is added in this figure. So if we randomize the data, then the RMSE will be increased as compared with the systematic design. So it means that the best design, maybe, we should not use the randomized design. So any other experiment is also the same. This is also the strip trials with many replications, but the randomized design had the larger errors. So as a result, what we have to do is that we need to apply the replicated systematic strip trials like this. So if you have the large field and to conduct experiments, then the strip trials with many replication is the best choice to know the treatment effects. And here is the linear mix model, but maybe the time is very limited. So I I will skip this slide. Yes, I will skip because this content is I have already talked. I have already discussed in the different webinars. So you are interested in my this statistical analysis, you can watch it. And later I will share that link. But because this content almost the same as that in the webinar. So, but I would rather to show the specific example of the on-farm experimentation in Japan or any other country. So now I have already presented the importance of the experimental design and the statistical analysis. So now we are working on how this kind of on-farm experimentations can contribute to crop productivities or farmers' income. So here I'm showing the case study of on-farm experimentations in Japan. This is the rice transplanter. So the major cereal crops in Japan is rice. Maybe it's almost the same as the Indonesia. And now the Japanese farmers are using the transplanters to grow the rice. And this transplanter, this is very general one. And it's very easy to adjust the rate of the fertilizer applications. So every turning point, I let the farmer to change the rate of fertilizer. For example, from 45, so it means 450 kilograms per hectare to 550 kilograms per hectare. And overall, we changed the rate with the rate of the base of fertilizers with the strip trial. And then now we in Japan, the small size yield monitor is not frequently available. So we use the UAV remote sensing and deep learning techniques to predict the rice grain yield to know the within field variabilities of the crop yield. So we use the multispectral cameras, and it provides many bands of the data sets. For example, green, red, and reddish, and NIR. Many types of the different types of the wavelength can be assessed using the filter. So then I use the deep learning model to predict the crop yield by using these images directly. So this images contains a spatial feature within it. For example, this area, high value area, maybe this is the high, for example, high nitrogen content of the leaves is clearly identifiable from these images. But if we average these values, it is meaningless. We lost the spatial feature of these images. So if we use the account of the deep learning techniques of the CNN, convolutional neural network layer added in the model, then it can automatically and efficiently extract the spatial feature, which is very relevant to crop yield. So it has much more efficient and more precise, it can provide more precise results as compared with the previous traditional linear regression model. So by using this multispectral images, we can predict the crop yield like this. There are 3 fields, and one field has them about 1.8 to 2 hectares around. So each dot indicates the different crop yield. So it's very efficiently providing the crop yield by using the UAV remote sensing. So after applying the different rates of fertilizers, then we can assess the yield using UAV. Then we can analyze the relationships between the fertilizers and the inputs of the fertilizer and the crop yield. So here I only show the 2 examples of the field 1 and 2, but we have already conducted more than 10 fields across these 2 or 3 years for the on-farm experimentations with farmers. And as you can see, the field 2 is very obvious that there is no relationships between the fertilizer inputs and yield. So yield did not respond to fertilizer. And in the case of field 1, the yield is increasing by 0.21 tons per hectare if the rate of the fertilizer is increased by 50 kilograms. But if we consider the profits, the the variable cost of the fertilizer is much expensive than the revenue or by the enhanced crop yield. So if we increase the fertilizer rates, if the farmers increase the fertilizer rates by 50 kilograms per hectare, then the farmers will lose the profits of the 49, about 50 US dollars per hectare. It is not little if the farmers are farming a large scale, because this farmers now is managing more than 300 hectares per year. So, and many Japanese farmers, maybe this is not only for Japanese farmers, but also the other farmers, any country's farmers, who wants to increase the yield by increasing the rate of fertilizers if they have much money. But in many cases, there are not significantly positive effects on increasing the profits. So if we could accumulate more data sets from many regions or many countries, we can provide an evidence that increased yield. If you want to increase the yield, you don't have to apply much fertilizers. It's meaningless, rather than it's negatively impacts on the farmers' revenue or income. So we should reduce the fertilizer. And this is the results from the ADAS UK. ADAS is the agricultural consultancy companies, and they have conducted many on-farm experimentations, and mainly focusing on the wheat or barley. And this is one of the examples of the relationships between the crop yield and the greenhouse gas emissions derived from the fertilizers. So as you can see, this figure explains this yellow points indicates wheat or barley, so cereal yields, and then this blue or this bar indicates the GHG emissions. And mainly this GHG greenhouse gas emission, the amount of greenhouse gas emission has been calculated by the model. So most of the N2O is emitted from the nitrogen fertilizer that is applied in the field and not efficiently used. So many inefficiently used fertilizer is transformed into the N2O, which is the very important GHG. So as you can see, this is the yield. So we often expected that the yield can be increased by increasing the fertilizer rates. So it means the rates of the GHG will be increased. But as you can see, the yield data and the GHG emission is not relevant, rather than the yield is less in the high GHG gas emission field. So I suppose that the many farmers prefers to use massive amount of the fertilizers to increase the yield, but it is not effective for most fields. Rather, it increased the risk of the generating the GHG gas, so greenhouse gases. So from the perspective of environmental friendly and agricultural productions, fertilizers should be reduced, and that amount, how much amount should be reduced, can be confirmed from the on-farm experimentation. So this is one of the achievements of on-farm experimentation. Okay, so now let me introduce the second types of on-farm experimentations. The first one, an overall effect, and the second one is the site-specific response. But this must need the implements of the variable rates application technologies. So one of the famous farmers network and experimentations of this research is conducted mainly in US. And one of the projects called the Data Intensive Management Projects, which is led by the David Block, who is from the Illinois universities, and are conducting many experiments, many on-farm experiments. So they are all experiments are implemented with the variable rate fertilizer applications or the variable rate of seeding. And more than 60 farmers are now joining these experiments for every year. And it is not only in the US, but we can see many other countries, for example, in Argentina, Brazil, and the South Africa. So now this kind of network is enlarging from the domestic studies to the overseas study. And this project is aiming, the target is mainly the maize and soybean. And I'd like to show one of the example of the on-farm precision experimentations by this project. Maybe this is one of the big field, I think the 40 or 100 hectare of the single field. And by using the variable rate seeder, the seeding rates of the maize or soybean is variable across the fields. So the green area receives more seeds and the white colors receives less seeds. Then after seeding with the different rates, they can assess quantify the crop yield using the yield monitors. So this is the result of the yield monitors. And this kind of large field, they conduct experiments. So from this experiment, what we can know is that the best choice of the fertilizer rates for each delineated areas. For example, this is, you can assume that this area is 100 hectare. Then we can delineate the two zones. The one is low response area and another one is high response area. So the red area is a low response area. So if we increase the rate of the fertilizer nitrogen rates, then it will reach to the plateau of the enhancement of the yield. But high response area, so in this green area, if we increase the rate of the nitrogen, then it keeps going up to the top, to the highest yield. So in that case, each delineated area may have the different best choice to maximize the marginal profits. So so this kind of site-specific yield response can be varied across according to the management zones. So we could more efficiently manage the farmers' fields to spread the fertilizers or seeds in an efficient way. And now I'm also working on the similar project in Japan. I'm also using the variable applications. And now we are spreading different rates of the fertilizers for wheat production. Also like this is very similar work to the David Block. And now it's a minority, but a couple of farmers in some regions are now started to use the yield monitors. So I collect the data using the combined harvester to assess the spatial variations of the yield. So then we can use the kind of the machine learning model to estimate the nitrogen rates or the fertilizer rates to maximize the profits, marginal profits. Then what we can say that the farmer's rate is very constant. And farmers applying on 450 kilograms per hectare evenly and across all fields. But if they could apply the variable applications of fertilizers in more efficient way, in the best way, then they can gain more profits For example, $209 per hectare. So maybe one may think that this value is not so high as you expected, but this farmers is also now growing wheats for 120 hectares for every year. So if we multiply by all of the fields with these units of the attainable profits, then this value is not ignorable. So if you only see the 1 hectare in profits, it's not so high. But if you enlarge the farming scale, this little value is very important for the income of the farmer. So then, I'm so sorry, maybe the images is collapsed because of the problem of the PDF transferring. But now I want to introduce one of the great papers published in the Nature Food. Last year, one of the researchers from France, or maybe he is originated from France, and he studied in Australia. So her name is Lacoste, and published very informative and very interesting papers about the on-farm experimentations in Nature Food. So you can find this paper in the website, and it introduced how important the on-farm experimentations and how it could contribute to farmers' life or the surrounding enterprises. Because yes, so as I said before, the experiment is the one of the flowchart from the hypothesis setup, the running experiments and analysis and the interpretations. This is the one of the flow. But in this flow, there are many people engaged in this project or the discussion. So not only the farmers, but also scientists and agronomists, and maybe sometimes agricultural machinery companies or the consultants in companies may join this circle to efficiently facilitate the implementations of on-farm experimentations. So now, as this paper describes, there are many farmers' network to enhance the implementations of on-farm experimentations. Not only US and UK and ADAS or in France, maybe in China, there are some examples. And also Australia is also very famous for on-farm experimentation. And some countries in Africa. And maybe I have seen some word in Indonesia, but I'm not sure whether the Indonesia is engaged in. Oh, okay. It's all right. So another aspect of the on-farm experimentation is just this data sharing is very important. So today, because of the time of the limitations, I have only focused on the statistical analysis or the experimental design of the on-farm experimentations. But the results that is achieved or derived from the on-farm experimentation is not only for the single farmer. If we combine many data sets collected from the different regions or different farmers, then we can aggregate those data sets to make a new values or to make a new robust and precise model to know the causal relationships between the crop management and the crop yield. So only single farmers engaged in that on-farm experimentations, we only could gain 500 or maybe 1,000 of data sets. But if we include the 15 or 10 or 15 or hundreds farmers engaged in that research project, we could gain more than the millions or the billions of data sets. So it's very important to efficiently use such data by machine learning. So we hope that these kind of networks will be enlarging in the worldwide. Okay, so And also we'd like to introduce the last, so maybe this is not the last slide, but concerning about on-farm experimentation, this is the last slide. So the on-farm experimentation is may have the many directions. So in my field, I am agronomist and I'm good at, and I'm very interested in spatial statistics. So if we study the on-farm experimentations, I only focus on the data sciences or the agricultural sciences. Maybe I am the boundaries between them. But if we think the importance of data sharing or the management, then the social sciences is very important to implement such services or the make the additive values of the on-farm experimentations. So to facilitate the research in on-farm experimentations, we have to combine the many disciplines of the research, and of course social sciences is very important. And we are outside. I am an outsider of this research scheme, but and in the futures, I would like to cooperate with many researchers to conduct the on-farm experimentations in Japan and in other developing countries. So yes, I'd like to share the links for the good webinar and the conference. This international conference is only concerning about the on-farm experimentations, and it has been already closed last year. This is the first trial. And you can use the SHARP OFE 2021. If you search for this word, you can find out the websites of the on-farm experimentations. And yes, so even though you are not attendees of this conference, everybody can watch the pre-conferences webinar, workshops. So there are 4 parts of the workshops. The one is the value creations, and the 2 people and processes, and the 3 data analytics. And I also gave lectures or gave the speech in the data and analytics. And also there are the policy linkages. So social sciences is more important than the data analysis, I think. And because the theme 1, 2, and 4 is much relevant to the social sciences. So I've already talked about 1 hour and 10 minutes. And yes, maybe what I would like to say is that the on-farm experimentation is very prevalent, and now it's enlarging in the Western countries, where the large-scale farming is very popular. But the smallholders, like Indonesia or many mountainous area of Japan or any Asian countries, and of course including Africa, many developing countries and Asian countries are still. There are many smallholders. So now the smallholders are outside of on-farm experimentations, because farming scale is very important to adapt the digital tool of the agriculture. For example, yield sensor is very big, and it can only equip with the large combine harvester. But if we could quantify the rice yield ubiquitously, then we can conduct on-farm experimentations by integrating the yield data and treatment data from many smallholders. So now, in the last few slides, I'd like to present some good example of the yield quantification application system without the yield monitors. So now this application is just developed by the Kyoto University and the Africa Rice, CGIAR. Now, and they are developing a deep learning based model. So if you capture using the digital camera, or maybe using your smartphone, it's okay. Taking this kind of captures for the rice canopy, then we could know how much yield is in there in that picture. And this model is has the more than 5,000 training data sets of the pictures and the actual rice yield, and the grain yield can be estimated without harvesting. So if you take the pictures, then you can easily get the yield data. And now the application is released as the name of the Rice Scouter, and iOS Android application is available. Okay, I will pass this one. And this research is conducted by the Kyoto University and Rice Africa, but many countries across the world is joining this research project. And also GIF University also joining this research project, and I provided some data sets. And now the application is available. One of the way is to join or add the friends in the line. So I suppose that the Indonesian people are still, some Indonesian friends are using the line. So if you're interested in, you can read this, scan this QR code to add the line boards. And if you upload the images of the rice, then it automatically returns the yield from that images. So in that way, you don't have to harvest the rice, but you could know the yield. So then if you use the smartphone, the images have the geotag of the EXIF file, which contains the location of the photos where it has been taken. So many yield data points can be pinned in the maps, so that which farmers could gain how much yield you can visualize spatially. So, for example, if you unite kind of the farmers network, then one farmer reduce the fertilizers and another farmer increase the fertilizers, and you can compare with many data sets. So I believe this kind of the easily implementable services for quantifying the crop yield is very useful to implement the on-farm experimentations in Asian countries. Okay, so if you're interested in this application, you can use that line bots, but you can also contact this Twitter or maybe Gmail address to install the iOS and Android application. So thank you very much for inviting me as the speaker of this lecture. And if you have any questions, please don't hesitate to give me any question. Thank you.
Thank you very much, Tanaka Sensei. It's very awesome. Awesome, awesome, and awesome. It's 3 words for you today.
Thank you very much.
Because it's a very big idea about the on-farm experimentation, but you can exactly in 1 hour only, you can share with us about the experimentation on farm with the digital agriculture. It's very big knowledge about the precision agriculture, especially to apply it on the farm experimentation. So thank you so much for your kind presentation, Dr. Tanaka. Well, great. Thank you so much. Okay, we will go to the next session. Is the question and answer, Q&A. Wait a moment. There is any questions on the chat box or raise hand with or directly to ask to the presenter, to Dr. Tanaka. There are many participants have joined in this event today. We fluctuated from 140 until 170 audience have joined with us. There are mainly from our students in agriculture and biosystem engineering. Also, there are our colleges in agricultural faculty, University of Lampung. and our college is also in Indonesian Agricultural Engineering Association, Perteta. Ada Bu Leni Saulia. How are you, Bu Leni? Also, I think this is the great presentation, because when we, especially for our students, they took some course, especially in experimental designs. It's very important to learn from Dr. Tanaka presentation. Also, there are methodological research and agronomy aspect, I think. Also data analytic with programming with R or Pythons is a machine learning support for digital agriculture. Okay, chotomate. Wait a moment, this is Japanese word, sorry.
Tracy-san, maybe we've got some questions from the chat.
Okay, I will.
One question.
Okay, there's there one questions on the chat box from El Hamida Reskia. Indonesia is a country with a very diverse topography. Are there challenges to apply this technology in extreme topography, like a high slope, maybe sometimes a lowlands area in Indonesia? It's very varied spatial distribution, because Tanaka Sensei said in the presentation, with the various spatial distribution, it's a very maybe challenging for us to get the data and how to analyze them. Please, Tanaka Sensei.
Yes, so I think in such fields, they still didn't use the combine harvester. Maybe they have to harvest the rice manually. So in that case, just like I presented in the last few slides, maybe the local farmers can quantify the yield by using the smartphone applications to quantify each field and yield. Then if we model the relationships between some crop management and the crop yield, then we must include the effects of the topography, and the elevations, or maybe we can count the number of the stages of the terrace. So we should include such factors in the modeling. And this is very interesting, the topics, because I have already, one of my colleagues are very familiar with this in this aspect, because this is not the case of the Indonesia, but one of my Japanese researchers is studying in Laos, in the terraced paddy fields. There are still many, there are very strong trends of the crop yield from the lower lands to the upper lands. So the lower lands receive much nutrients or the resources from the upper field. So the high fertility could be found in the lower land. So there must be some graduated yield variations in the terraced or the very complicated topography. So these aspects should be included in the modeling. But it could be attainable if you assess the crop yield. The difficulty is how to collect the data sets of the yield.
I see. Yeah. Because the data is on the field is very variative, and sometimes we cannot to make the models, to make a model on the field. There are many parameters. We cannot make a model sometimes. This is what do you think? What do you think about this?
At least if we could quantify the rice yield from each field, then we can establish the model by using the geographic relationships. What I mean is the topography can be used as explanatory variable. So yes, but the must is to quantify the rice crop yield.
Yes.
Well, maybe we can use the satellite imagery as well to establish the crop yield.
See. So I think this geographical information system is very important to make information, spatial information like this. Because in our department there is one topic lecture about GIS, geographical information system application. So it is very important for us to. Sorry, can mute Wahyu, or you want to ask question? Okay. Yeah, because GIS is very important to make. Because in the first slide you said there are some step like data collection, and then interpretation and application. Yes. So it's the first important to make data collection first to make. But it's only the technology sensory only, I think, because Japan I think is support with the high technology support in your research. Also in Indonesia, we'll now start to apply the technology sensory in our farms. Yeah, because this is the key to get the data from the field, and after that we can interpret with the data analysis. This is your core. I am very appreciate your expert in this data scientist, because it's very popular in the world now. Is data scientist is very high fee for this. High fee for their salary in the company, because the data scientist is a very high rate for their salary every month they got in their company. So our students, please keep fighting to learn about the data scientist. You can insightful from the Tanaka Sensei in here this moment. Oh yeah, Tanaka Sensei, your book about the precision agriculture is available online, so we can buy your book.
No, book. No, I just mentioned the webinar. You can watch the webinar.
See. I think this is some book or chapter books about the precision agriculture.
No, I have not published yet.
So I can buy, or we can buy it in the online.
Please wait for 5 or 10 years. I still didn't write any paper.
Because it's a very interesting, especially in my research area. Yes. Okay, there is any comment or question? Okay, we do have one question again from Supriyatin. This is my colleague, my friends, Supriyatin, Dr. Supriyatin. Yes. Is it possible to use the rice coater application to predict the yield of rice farms in Indonesia? Because you said this is applied in your country in Japanese only, or we can apply it in the Indonesia, because Indonesia has not joined the on-farm experimentation research in your research center. Is it true that the output of on-farm experimentation or the application can only be used in the area that are already joined in the OFE, since it's related to the precision agriculture? How about this, Tanaka Sensei?
Of course, it's possible, because the on-farm experimentations and this application is independent. So the line, I don't know whether that's the language is adapted in English, or maybe Indonesian language may not be adapted, of course. But yes,
because the line in Japan is Nihongo, yes.
Yes,
in line.
In line, maybe you must use Nihongo, Japanese, but the application version, I heard that there is the English version. So specifically, you should ask to the contact address, one of the enterprise on the R1 Technologies. That company is now coding making that applications. Now it is for free for using, and now so basically this application is developed in the Africa, so to improve the crop productivities for the local experiments in the African rice production. So it will not take any money for using that applications. So if you are interested in that, you can use it.
Ah, I see. So I think so. Did you mean we can use this application?
Yes, yes. And now that's the application developer is looking for some cooperative researchers worldwide to collect more data sets. So now I remember that's now there's 7,000 or maybe more than 5,000, so 7,000 or 8,000 rice yield observations, but we still have to increase number of the training data sets. And maybe there is not much available data sets in Indonesia. So it's very welcome to join to use that applications and to share the data.
Oh, thank you very much for data about the application rice scorer. So Ibu Supriyatin, we can use the rice score application in Indonesia because as for information, Indonesia is a huge application paddy field area in Indonesia. It's very big, so it's very important for us to implement the on-farm experimentation with the digital agriculture. Yes, to make easy for us to improve our quantity and quality of our products in rice field or another implementation in the farms like this. I have one curiosity when your presentation about the strip field. Yes, strip field. You applied in the variation of fertilizer 45, 50, 55 on the strip. That is a one block of paddy field area or farming area, or you separate it between each of treatments. Do you separate it every each of field? Because when I saw your presentation, there is no separation between strip in one block.
Separation is what do you mean?
On the tractor weeding sowing the tractor. There is some coloring of the strip field. 19. Hey, sorry. Yes, 19. Yes. This is strip tile design.
Yes.
When I saw in the slides, this is the coloring 45, 50, 55 kilogram per hectares. This is any separation between each of treatments 55, 45, or 50, because when we apply the different fertilizer in one block, maybe the water will be influence the distribution of the fertilizer on the field because the irrigation.
So this transplanter is submerged the fertilizers into the soil. So the fertilizer wouldn't be how to say move in the water. So directly dig the ditches and they put the fertilizers in the deep soil. So it wouldn't move.
So you taking in on the subsoil, yes, not in the surface.
Yes.
Not the surface. Yeah.
Yes, not in the surface.
I see. Okay. Because when you say the spreading fertilizer, it become lost.
Yes.
I also the comparison when we apply to distributed directly to the whole of the plants nearby the plants, not the distribute what is this special distribution with the directly to the plants. This is a different different of the losses, or we can improve with the directly to the plants.
Pardon. Can you give some again?
Yeah. Yeah. On the presentation, you said spatial distribution fertilizer. We got the losses, our money. Yes.
Which part?
So this is. Forgot. Yes, this one. Ever spreading loss. Yes, this one. Yes.
Yes. So if we could optimize the spatial distribution of fertilizer spreading, then the farmers can gain more this profit. So, but we can see this rates. This is optimal rates of the nitrogen. Other fertilizers, then the optimized one is mostly less than 450. So in this case, is also as same as the previous cases of the rice. The fertilizer rates of the farmer's constant rate is much higher than the optimum rate. And some areas we can reduce much. We can reduce much more. For example, there's 450, more than 450 rate can be observed very small rate areas. 540 is also maybe there's the minorities. The majority of the area is 360 or 270. So 270 is maybe less 60% less than the farmer's rate. So yes, now the not only reducing evenly, but also some areas should be reduced more. Should be reduced with more less fertilizer.
I see. Okay. So this is the key point. Not every additional fertilizer can improve the.
Yes.
So this is like a polynomial graph, or there's a some get down after the optimal condition. So this is important to make a model. Yes. The model to optimize the model for fertilizer input for our farms. So this is an interesting topic. So, but the time is limited for us to discuss more because panitia masih ada waktu because this is the time is limit. Yes. Okay, there is no question again. I think it's enough for today. Yes, for presentation from Dr. Tanaka and also the question and answer. Thank you very much. We do appreciate for participants for sharing this question and attention for this event today. If you have any question or sometimes you can email us in this moment, so you can directly to the Tanaka Sensei. Okay, we'll just briefly thanks to Dr. Tanaka for giving lecture today. Give applause for our guest speaker today. It's very inspiring for us. The lecture are very awesome for Dr. Tanaka Sensei. Thank you very much, Sensei. I'm sure.
Thank you very much, Tristan.
Okay, I hope we will meet again. Maybe in Indonesia or in Japanese again in Gifu University. Also, we will meet again with the other colleges. We can making strong collaboration research between Gifu Daigaku, Gifu University, and Lampung University, because we have a cooperation MOU between Lampung University and Gifu University. So,
if there is someone who wants to apply for the next scholarships, maybe you can find me. If the students are interested in agronomy or this kind of the digital agriculture or precision agriculture.
Thank you very much for information.
But that has been already closed for this year. So
yes,
next year.
I know. Because this is, I think this is a small number can accept the max scholarship, I think.
Yes, no,
Yes.
2 or 3 students.
Yes, because it's very competitive today, and the funding is very limited also every year. So okay, very soon our students. There any chance for Tanaka Sensei about the students exchange, or maybe if you want to continue to master study in Gifu University or doctoral study, Tanaka Sensei has informed us to give open hand to directly register to the Gifu Daigaku. It's nice. Okay, I will present the certificate award to you, Sensei. Thank you very much for your time.
Thank you very much.
Yes, I'm sorry to disturb your time today. I am now very busy because it's Tanaka Sensei is a very productive person. He's got awards from Japanese. I think I forgot. You got some Young Scientist Award this year. Yes, Young Scientist Award
thank you very much.
for
Yes,
farmer-centric on-farm experimentation. So this is the data scientist. I should be learned with you about the data scientist to improve our research in the next future. Maybe we can make collaboration. Thank you, Tanaka Sensei. This is your certificate award for the invited speaker in recognition to your participation on international lecture on agriculture and biosystem engineering in number 5 series. So we can enjoy. I hope everyone enjoy these moments, so we can share together about our research, discuss in the next future. Thank you very much, Tanaka Sensei. So I will hand over this event to the host or MC, please. Thank you very much.
All right. Thank you, Mr. Ahmad Tusi, PhD, and Mr. Takashi ST, PhD, for the insightful presentation. Well, the next agenda is awarding certificates to the guest lecturer and photo session. So, please to all participants, may turn on your camera.
Ini masih apa share screen tuh, ya. Oke, sudah siap? Ada apa-apanya, Bang? Sudah? Beri apa-apa?
Okay, slide 1, 2, 3. Slide 2, 1, 2, 3. Slide 3, 1, 2, 3. Slide 4, 1, 2, 3. And that have been implemented. Hopefully, it will be useful for us. Finally, I would like to say thank you for your participation. Before we officially end, please note that the international lectures will be held again on March 2022. Make sure you mark the date. In the end, I am Fitria Amelia Damayanti signing out. Thank you and see you.
Thank you. Thank you, Tanaka Sensei.
Thank you, Tusi-san.
Terima kasih Bapak Dekan, Prof. Iwan Sukribanua atas kehadirannya. Terima kasih banyak. Terima kasih banyak pada rekan-rekan semuanya yang telah hadir pada International Lecture hari ini. Rekan-rekan semuanya, para mahasiswa Bapak yang saya banggakan semuanya. semangat, tetap semangat, terus belajar. Ini ada peluang luar biasa ke depan, tantangan luar biasa untuk generasi milenial kita ke depan. Insya Allah siap. Sampai jumpa pertemuan berikutnya. Tanaka Sensei, see you in the
See you soon.
see you soon. Get well soon.
Izin les, Pak.
Langsung editing.